Okay, so this lecture is on 10.4, divergence and integral test. And before we begin, let me just remind you and summarize what we've done so far. Okay, so infinite series is a sum of an infinite number of numbers. And now, to find that sum, right, we find the sequence of partial sums. Right, so find or let's write form. Of partial sums. And then we compute a limit of that sequence. Okay, so let's do one example that we've seen before, but let's do it anyway. Okay, so infinite series. So let's take this geometric series from n equal 1 to infinity of 1 over 2 to the n. I know we've done it already probably twice, plus 1/4, plus 1 over 8, plus 1 over 16, plus. Okay, so this is our infinite series, and here here's the sequence of partial sums. Right, it's called partial sums because we add on certain blocks, right, or certain sections of the series, right? So first term in that sequence would be half, and then these two added, and then these three added. So that will be my sequence, right? So I have half, 3/4, 7/8, etc. All the way to that formula, right? The explicit formula that gives us that sequence. Okay, so now we compute the limit of that sequence. Okay, so limit with n approaching infinity of s n, s sub n. So now I have that explicit formula in there. Right, and we already know that it equals to 1. Right, we can separate it into two fractions. This fraction would be 1, and then this fraction would tend to 0. Okay, so 1 minus 0 is 1. Okay, so this is the sum of that series, of this series, right? Sum of this series. Okay, and that's that's the point of this whole thing. Okay, let's review the notation and a couple other definitions. Alright, so infinite series. Alright, so we have that infinite sum from n equal 1. It can be any number here, right? To infinity, a sub n. So we have those individual terms. Okay, so now nth partial sum. Sub n plus here. Okay, so S1 to A1, S2 will be equal to A1 plus A2. Well, let's write one more. S3 will be A1 plus A2 plus A3. So Sn would be what you have here. Okay. Now let's put one more thing here. So that will be the sequence of partial sums. Okay, so we have that S1, S2, S3, S4, all the way to Sn. All right. So the main point of this lecture is to figure out, given a series, right, is to figure out whether the series converges or diverges. Okay, so we look at a couple ways of determining that. The first one is divergence test. All right. And sometimes, you know, when you're given a sequence, series, you can simply see, right, what's going on, where that series is going, whether it converges or it diverges. For example, this one, right? So you have 2 to the nth power with n going from 0 to infinity. Alright, so I have 2 to the 0, which is 1, 2 to the 1, etc. Right, next one is 8, and it's easy to see, right, that the sequence diverges, or series diverges. Okay, and the reason is, let's write it down. The individual terms are not getting closer to 0. They're just growing, right? So if you're adding terms that are getting bigger, then obviously that the sum of this series goes to infinity, to 0. Okay. So let's put it in some formal way, in the form of a theorem. So let's just write, if the series and from 1 to infinity a sub n converges, then, right, those individual terms tend to 0. Okay, so this means terms tend to 0. Okay, just note that the converse is not necessarily true, right? Meaning that if the terms tend to 0, it does not mean that the series converges. Okay, what this means is that basically is that if that limit with n approaching infinity, if they don't tend to 0, then the series diverges. If they do tend to 0, we simply don't know. And I'll show you in a moment, I'll show you a sequence where the terms do tend to 0, but the series doesn't converge. Okay. So let's look at a couple examples. Something like this. So from n equal to 0 to infinity, and the formula looks like this. So now, and if you start plugging those integers here, right, in place of n, you're gonna get 1, and then plus -1, or we could write -1, plus +1, -1, etc. Right, so you just look at those terms and you can see that they don't tend to 0, right? They don't get closer and closer to 0. So our conclusion is the series diverges. Okay, let's look at another one. So here I have again a sum, this time from 1 to infinity, and here I have 7/6 to the nth power. Okay, and let's write a couple terms. So if n is 1, I'll have 7/6. When n is 2, I'll have 49/36. And then it keeps going. Okay, and just like with this one, right, we can see that the terms don't get closer to 0. Also, right, this is a geometric series with r is bigger than 1. Right, so geometric series. R is greater than 1. So our conclusion is the series diverges. Where's my green? Here. Alright, so I hope you see what's going on. Let's do one more. So example 3. Okay, something like this. A sum of n with n equal 1 to infinity to n/n+1. Okay, so let's write a couple terms. So for n equal to 1, I'll have 1/2, and then plus, when n is 2, I'll have 2/3, and then plus 3/4. And I hope you see what's going on. We could write, how about this term? 1000/1001. So I hope you see what number these terms approach, right? They approach 1. But 1, of course, is not 0, right? So the terms are not getting closer to 0. So the terms don't tend to 0. So our conclusion is diverges. The series diverges. And we're done. Okay. So now question, right? So we said if the terms don't tend to 0, right? We basically say the series diverges and we're done. Well, what happens if the terms do tend to 0? Well, we based on this theorem, we simply don't know, right? So we need to figure it out one way or the other. Let me give you an example of a series that whose terms are approaching zero, but we simply don't know what happens with that, with the sum of that series. So example 4. And this is a harmonic series. We'll be using this example quite a bit, and it looks like this. So n equals 1, infinity here, and it's 1 over n. Okay, so let's write a couple of those terms. So the first one is 1 over 1, and then I'll have 1 over 2, 1 over 3, and it keeps going. Alright, so you can see that the numbers are getting smaller and smaller, the terms, so they do tend to 0, but we simply, as of now, we don't know, right? Okay. So let's leave this series for now. Let me give you more examples, maybe a little more interesting. So example 5. So this one is from 2 to infinity, and we'll have n squared here, n squared minus 1 here. So as usual, let's write a couple terms. So for n equals 2, I'll have 4 here, and here on the bottom I have 4 minus 1, 3. So I can already see that I will not be getting closer to 0. So here I'll have 3 squared, which is 9, and 8 over here. Okay. So our conclusion diverges. Alright, example 6. It's 2 parts. So the first one looks like this. So from n equals 2 again to infinity, and the formula looks like this, so negative 2 over 7 the power of n. Okay, so here, and if we write a couple terms, we would get what? If I get n equals 2, I will have, or is it 4? I don't know how to, I mean, I know how to, but I don't know what 7 to the 3rd power is. I'm not going to do it, and I don't have my calculator here. Anyway, so the first term would be 4 over 49. So you can kind of see, right, that the terms are getting closer to 0. And, well, if you look at it closer, you can see that this is a geometric series. So, based on the fact that the terms are getting closer to 0, right, because the denominator will get bigger faster than the numerator, right? So I'll be dividing smaller number by bigger numbers, right? So definitely the terms are getting closer to 0, but based on the theorem I just gave you, right, we cannot tell. But we can tell from the fact that this is a geometric series, right, and that r, right, is between, was supposed to be between negative 1 and 1, and it is. So our conclusion is that the series converges. Let's do, what do I have? I have one more. So example 7. And after that we'll go back to the harmonic series. Okay. So this one looks like this. So it's a sum. And with n equal to 0 to infinity. And this time we have a trigonometric function here, cosine of 1 to the power of n. Alright, so how can we analyze it? Well, this is simply a number, right? So cosine of 1 is equal to about 0.54. And our conclusion is, well, since this is 0.54, right? It's not exactly 0.54, but we definitely see that that this number, this cosine of 1, is between 0 and 1, right? So this is a geometric series with r between 0 and 1. So let's write that 0.54, even though it's not really 0.54. This is an approximated number. And our conclusion will be the series converges, because geometric series and absolute value of r was less than 1. Okay. Well, actually we can figure out what the sum is, right? So we have that formula at a over 1 minus r for geometric series. So a is 1, and here I have 1 minus that cosine of 1, right? So we do a little bit of arithmetic and we get some number like this, also approximated number, 2.1753. Alright, so the series converges and this is the sum. Alright, so let's stop here, and next time we'll look at that harmonic series.